In the previous video, we have studied this very interesting quadratic assignment problem, and we have seen something a little bit special there because we were indexing a two-dimensional array by two decision variables xi and xj. And this method is a factory method that will create an element constraint for us, and it will post the element constraint for us. And this element constraint looks like this. It has a signature receiving in the constructor an array, a two-dimensional array of integers, variable x, y, these are the two indices variables, and z is the target variable. And it will enforce the relation t at the index x and y is equal to the variable z. The goal now is to create an efficient propagator for that constraint. And the first question that we should ask ourselves is, do we want to create holes in the middle of the domain of z? And are we fine with creating holes in the domains of the variable x and y? Which one is the most interesting? To answer that question, we should consider the fact that the result of the element constraint here is involved in a sum constraint. Okay, so it means that the variable z there, eventually they will be added in the sum constraint, and on sum constraint, as you know, we can only perform bound consistency. So it's not very interesting to create holes in the domains of z, but it's interesting to create them in the middle of x and y because these ones are involved in an all different constraint, and we can use that to filter the all different constraint. Okay, let's study the propagators for that constraint, and first we will illustrate that on a small example. That's the two-dimensional array there, and you see that the indices are represented here, so 0 to 3 and 0 to 3 for the y variable. What we will do is that for each index, for each entry, for each cell of the two-dimensional array, we will create a triple there in this table, right? So, for instance, let's consider this triple, okay, for that entry. You see that it's at index 0, 1, and we have the value 8, and you can retrieve it there. So you've got 8, 0, 1, okay? So that entry there in the table corresponds to this cell, okay? Because there is the value 8, there is the index 0, and there is the index for y, which is there, which is 1, okay? We sort the entries of this table increasingly according to the first column, which is the value z. The domains initially for x is 0 to 3, for y is 0 to 3, and for z is 1 to 9. So clearly, you see that every possible there entry, every combination of x, y, and z, for every combination of them, there is a solution in that constraint. What can happen now is that there is an update on the domain of the variable z, and the value 8 and 9 were lost, and now we have a maximum value for z, which is a 7 there. Okay, so let me first speak about the state that we will maintain in the propagator, in the filtering algorithm with that constraint. I will have here a counter that represents the number of cells that are still valid on the columns, and here I have a counter that represents the number of cells that are still valid on this specific row. Okay, so it's 4 initially everywhere. Okay, and I will also have two pointers, the low and the up pointers. That tells me that all the entries between the two are considered as still valid possibilities for the table, for the element constraint. So now that it has been updated to 7, you see that the 9 there is not a solution anymore. Therefore, I have colored this cell in red to say that it's not valid. So it means that I need to update my upper counter, and so I will move my upper counter, I will decrease it by 1, and it will become this one, okay? But it's still not valid. But while I was doing this, to reflect the fact that this is a gray cell, I have also updated my column counter and my column counter there, because they lost one cell each of them. So now it's a 3 and now it's a 3. I continue like that. You see that the cell that we just lost is this one, and I have updated the counter, the row counter, the column counter appropriately. Okay. I continue like that. I decrease my upper pointer. You see that I'm still updating the row and the column counters. And at some point, something very interesting will happen, because now if I'm about to lose this one, it's still not valid because my maximum value for z is 7. When I will update the fact that I'm losing this row, this cell, this corresponding cell, which is this one, the counter there will become a 0. If the row counter becomes a 0, it means that the value 2 will be lost there. And so I will be able to prune and to remove the value from the domain of X. Okay, you see it's a 0, and therefore I remove it there. Okay, but 8 here is still not it's still not a good solution. Okay, and so I move it like this. I decrease it again. You see that I lost again a value there. Now I lost the value 2. Okay, I lost the value 2 from X because I have a counter here that became 0. And then I stop. I stop there because you see that 603 is a green cell. Everything is fine there. That corresponds to this one. Okay, this one is a valid support. You see that 6 belongs to the domain of Z, 0 belongs to the domain of X, and Y belongs to the domain of Y. So we stop. But we stop on a 6, which means that I can also update the value there and update it to 6, because it means that the first opportunity to stop was on a 6, and I never met a value 7 which was valid, so I can safely remove the value 7 from the domain of Z as well. What happens now if we update the minimum value of the domain of Z? In that case, I need to increase the lower counter if the lower counter is currently on something that is not supported. And it's the case here because it starts on a 1, but 1 does not belong to the domain of Z. So I can increase the lower counter by 1, and I should reflect that on the row counter and the column counter. Okay, so that's the entry 0, 0. So that's this one, and so we will replace this by a 2, and we will replace this by 1, like this. But now we do the same for this one and this one, and suddenly we realize that the counter is a 0 there, and so we can safely remove the value 0 from the domain of Y. Okay? And we continue like that, and we stop whenever, again, when everything here is green, and when we stop, it's on a 7, on a 4, or on a value 4 for Z, and so we reflect that there by pruning the value 2 and 3 from the domain of Z. These two counters, okay, so, well, this one counter per row and this one counter per column will be stored as state integer. Okay, that will be state integer. Okay, and these two pointers will also be state integer. So all that will be of type state integer, so that when you go down in the search tree, you will only remove value, and so you will only decrease the counter. You will only increase the lower counter and decrease the upper counter. Okay, but when you backtrack, you need to recover this value as they were in the state of the node. Therefore, we use a state integer so that the state manager on backtrack, when it will restore the state, will recover all the value as they were in the previous node. Let's study the implementation now of this constraint. So the element 2D extends the abstract constraint class. That's not surprising that we store here the array T. We've got the 3 variables involved in the constraint. And then we've got the number of rows, the number of columns. We've got the row counters and the column counters. As I mentioned, they will be state integers. And that's the same for the low and the up counters. And finally, we've got our flat array of triples that I will call zxy. Okay, that's the identifier of my variable zxy with the name of the columns that you can read there. Okay, to make sure that we know in which order they appear. When do we want to be notified to call the propagate method? We will hook up this constraint on any modification of the domain of X and Y. And we only want to be notified when something changes in terms of bounds of the domains of Z. Okay? We are not interested to be propagated when a value is removed in the middle of the domain of Z. Okay? Only on the bounds. That's the propagate method. And the propagate method, okay, that will be our table. So we've got the table zxy, and we've got here the lower counter, let's call it L. And so this propagate method will be interested in increasing the lower counter gradually in that direction. Okay. Every time we realize there is something with a red that is not supported, we do L++ and we update it and we move it to the next one. Okay. That's what we do in this while loop. In this while loop, if we realize that at the current position L, we are still less than the minimum of the domain of Z, then we increase the counter by 1, okay? But then it means that possibly this row, we need to do something for it, okay? Because the value that we have there and there will be lost, and we need to appropriately update the row and the column counters for this specific entry in my array. And so this is what I do there by calling the update support there. I call update support to notify that this row was lost, and I will appropriately decrement the row counter and the column counter here of the corresponding entries that I just lost by updating the lower pointers and moving it to the next one. Okay. If we see that the counter becomes a 0, of course, we also remove the value from the domain of X and the value of Y. That's the whole point of maintaining these counters, is to be able to incrementally remove the domain of X and Y as soon as we realize there is no support on the column or on the row of the table. Okay. Once we have done and we end up with something that is green everywhere for the value Z, X, and Y, we update the value of Z, the minimum value of Z, to the corresponding one that it has there. Okay, so we take at the index L the value of Z that will become the new minimum for the domain of Z. I do not show it there, but we will do exactly the same for the upper counter. Okay, but instead of moving it in from top to bottom, we'll move it in that direction. Okay. So that's a very efficient propagator. It will be able to remove values in the middle of the domain of X and Y. But as you see, we only update the bounds of the variable Z, so we do not remove anything in the middle of the domains for these variables. Though it's a kind of hybrid consistency. It's in between bound consistence and it's in between domain consistent. We cannot properly characterize it completely as domain or bound consistency. It's really in between the two. In the next video, we will study this version of the constraint, but for one dimension only, not 2 dimensions.